Okay. All right. So before the first lecture, I just want also to give you a few details about how the course is organized. So there are a few of us that will help you learn about the materials. So I will give you the theoretical lectures, but you can also count on François, Yann, and Victor to help you with the projects. Or if you have any other questions about deep learning, feel free to contact them or to contact me. All the materials, as usual, can be found on GitHub. So for this course, this is the URL. You will find the schedule, you will find the slides, the materials, the homeworks, and the project instructions. For the slides, if some of you are still printing them, please wait before the, at least the day before the lecture, because usually I make small updates before every lecture. So if you want to have the very last version, just wait for the day before. Or the same if you take notes on your tablet and on the PDFs, also make sure you have the last version of the PDFs. Okay? There is also, if you need or want, a Discord server on which you can ask all your questions. It's not very used, I don't know why, but it's there and we are connected. If you have questions, just feel free and we'll answer them also there. Regarding the materials themselves, so the slides should be sufficient, but if you need more explanations or another version or another way to explain the concept that we are seeing together, the only book I would recommend is this one, Understanding Deep Learning by Simon Prince. It's really a very good introduction to neural networks. It covers everything, or almost everything we'll see and more. And the book, you can either buy them to have a physical copy, but the book is also freely available on the internet. So if you go on the website of the book, the author is releasing the book freely also for you if you want. Okay, so this is completely legal. You can have the book by just downloading the PDF on the author's website. The videos, so maybe some of you have found that there are videos on YouTube. These are the videos which were made during COVID. They are quite out of date, I would say now. So this was 4 years ago. So they are still there, they are still online, you can watch them. However, what I will do this year is actually to record also the lectures that I'm giving in class. So you will find them after the course on Unicast. Okay? Projects. So there are two parts for the projects. First, the homeworks. So you will have two homeworks to complete, which are basically Jupyter notebooks, where we will guide you and introduce you to PyTorch and to setting everything up to train a neural network. So these homeworks will cover the basics of tensors and operations in PyTorch. Then you will have to build a neural network, a small convolutional neural networks, and then you will have to train it on a data set. Okay? So these homeworks, they are very straightforward, but I would really recommend that you do them. This is optional nonetheless, so if you are for some reason already familiar with PyTorch, fine. You can just skip these homeworks if you want. But if you complete them, they will account for 10% of the grade. Then there is a project, which is a much bigger programming project of your own choosing. And the goal of this project will be to apply deep learning, so to develop a neural network for a problem of your interest. So more details will be given later, but you can maybe already start thinking about interesting applications that you could try with deep learning. The evaluation, so there will be an oral exam in June, and this exam will account for 50% of the grade. So usually what we do is that you have a list of questions, you pick one randomly, and then you have to elaborate on the topic related to the question, like explain convolutional neural networks, explain diffusion models, basically one of the topics that we will cover in the course. And the projects will account for the remaining part of the grade, so 50%, depending on whether or not you have completed the homework. So if you did the homework will account for 10% and the programming project for 40%. If you've not submitted the homeworks, then the homeworks will not happen in the total, in which case the programming project will account for 50% of the final grade. Okay? The programming project is mandatory for presenting the exam, so if you have not worked on the project, then we will not allow you to present the exam. Also during the exam, after the theoretical questions, one of the teaching assistants will also ask you questions about your project. Okay? Do you have questions about how the course is organized? Yes? Will our exam be in English or French? Up to you. Usually it's in English. And I think it's a good exercise, even if you don't speak English very well, like myself. But that's fine. Okay? You will not be penalized if you make mistakes. Any other question? Oh, okay. All right, so for the next part of this morning, we'll go over the first lectures, which will be a recap on the fundamentals of machine learning. So you should be quite familiar with the content, even though you may not be familiar with the notations or the vocabulary I will use, but supposedly the concepts are something that you should have seen before. I will also already introduce a few concepts from deep learning, just to tell you about some differences which are quite important with respect to traditional machine learning. Okay, so we'll go over supervised learning. I will redefine what is supervised learning, and then the usual recipe to solve supervised learning problem, which is the empirical risk minimization principle. Then we'll discuss underfitting and overfitting, and finally we'll conclude with the bias variance dilemma. All right. So statistical learning, and specifically supervised learning. So the setting of supervised learning is to assume that we start first with a training data. We have a large collection of data, which we call a training set. And this training set is a collection of pairs of inputs and outputs. The inputs is what I will denote with X and the output with Y. Okay, so we have pairs of these inputs and outputs. And we assume that these pairs, they come from some joint distribution, P, X, and Y, okay, which is the distribution of the data, which we don't know, okay, but we make the assumption that these pairs, they all come from the same distribution, okay? The only thing that we get to see from that distribution are this finite number of realizations, okay? The inputs, we'll assume that they belong to some input space calligraphic X. Okay, usually this X will be described as vectors. Okay, that's what you should be familiar with in the case of tabular machine learning. We have a set of features or variables or descriptors or attributes, I don't know how you call them, but which you put all together into vectors. But in deep learning, you can be much more generic. You could have an input space of images, you can have an input space of videos, you can have an input space of graphs, anything that you want, as long as you can describe that mathematically. Then we have the output space, so for the Y values. So that will depend, of course, on the kind of task that you want to complete. If you want to solve a classification task or regression task, or if you want to make structured predictions. But for most cases, at least for today, you can assume that Y is a scalar. For example, it's a category, or just a real value. Okay, but later on, we'll see that we can have Y to be a whole image, a whole graph, or something with a structure if you want. We'll make also the assumption that the training data is generated ID, so identically and independently. that we have only a finite number of pairs, and we'll say that the size of this data set is n. Okay? And generally speaking, we'll not make any prior assumptions on the data distribution pxy. Okay? So this is the setup with these inputs and outputs. And then what are the problems really that we want to solve in this setting? Well, usually, supervised learning will be concerned with one of these two problems. And I suppose this is what we have seen in machine learning. You have classification problems in which we have inputs, usually that are described as vectors, and we have outputs which correspond to categories. Okay? And what we want is to build a model such that we can use this model to estimate at least the class y, so the category y, the value of y, which is the most likely given the input x. Okay? Now, formally, I can erase that. So I'm saying in this case that the product of the input and the output space, x and y, okay, I define it as the space of vectors of size p for the inputs times this thing, triangle C delta C, okay, which is what we call the probability simplex of size C, which means that I will encode the outputs, the categories, as vectors that I can interpret as probability estimates. Okay? Over the classes. So if we have C classes, this set will correspond to a set of vectors of size C, such that, so for example, we would have 0.1 for the first class, 0.2 for the second, and maybe 0 for the last, and we'll have C element, and each of these elements will be a number that we can interpret as a probability. Okay? Meaning all these values will be positive, and if we were to sum the values inside one of these vectors, it would sum to 1. Okay? And so all the vectors that satisfy these constraints, they belong to this set. Okay? Right? For regression, we have something similar, except that we replace the output space, so the probability simplex, in this case, just by the space of real values, R. Okay, so given some input x, we want to predict some real value y. Okay? So intuitively, classification will just consist in identifying a decision boundary between objects of distinct classes. So for example, if you have 2D points, like this one that you see, so each point will correspond to a vector with two values, okay, the coordinates of the points on the plane. And what you want to predict then is a color, red or blue, which you can encode, in this case, as a vector of two elements, and to which you associate the probability of belonging to one or the other class. Okay? And for regression, basically intuitively, the goal of regression will be to try to estimate relationships between variables. Okay, so in this case, maybe from these points that you see in blue, you would like to recover a curve like the one that you have in red. Okay, so that's the traditional way we define this classification and regression problems. The framework I will use throughout this course will be maybe a bit different. I will adopt the probabilistic perspective. And to me, supervised learning will always be framed as the goal of trying to estimate a conditional distribution. Okay? So and in supervised learning, the conditional distribution that we'll try to estimate is simply the conditional distribution of the output given the input. Okay? And so this is, in my opinion, a bit more generic than just saying that, for example, classification is about retrieving the class which is the most likely. The object that I will try to model instead is the whole conditional distribution. Okay? Or in the case of the regression, I will not be so much interested in trying to estimate only the expected value of the output given input. What I will want to estimate instead is the whole conditional probability distribution of over all possible y values given some input x. Okay, so this is the problem that we want to solve. Now, how do we solve it? So the recipe that certainly you have seen, maybe with some other name, is what we call the empirical risk minimization principle. So it's quite simple. Let's say you have a model, a function f, okay, of some sort, which may be good or bad, okay, but which is just a function which is already doing a mapping between the input and the output. Okay, and this function is produced by some learning algorithm. Okay, so for example, a function in the case of a regression could be a linear model, and the algorithm that you use would be, I don't know, some numerical optimization algorithm that you use to fit the parameters of this linear model. Okay? Now, there is the question, how do you evaluate the quality of these predictions? How do you evaluate the goodness of the model? So what usually we'll assume, at least in the empirical risk minimization framework, is that we have defined a loss, L, which is a mapping between ground truths and predictions to a scalar value. Okay, so we have a loss to which we can feed two values, the correct value and the value that we predict, and the loss will give us back a number which indicates whether or not this prediction is good or bad. Okay? So examples, for example, in classification would be a loss which takes as input some output, y, together with the prediction that you make with f, so f of x, and then produce either a value of 1 if your prediction is not the same as y, or a value of 0 if your prediction is the same as y. In regression, a common loss would be, for example, the squared error. And so there you say that your loss is the square distance, in a sense, or the square difference between the ground truth and the prediction. Okay? These are just examples for the empirical risk minimization framework. And already you should note that when it comes to deep learning, never ever will try to directly minimize this loss, at least for classification. You can try to minimize directly the 0-1 loss with a neural network in gradient descent. You will not be able to do that. Okay? So please, because every year in the oral exams, I have students telling me that, yes, if you want to train a classifier with a neural network, you should minimize the 0-1 loss. That's not something you can do. Okay? Instead, and that's something we'll see next week, the loss that we'll consider is the cross-entropy loss. Okay, but for now, at least for today, you just have to assume, okay, we have some loss L, whatever that is, and we'll try to minimize it. All right, so now that we have defined how we can assess the quality of a model F, we'll continue and we'll say that we'll denote by big F the hypothesis space, which is the set of all possible functions F that you can produce with your learning algorithm. The second part of the sentence is very important. We only limit ourselves to the functions that we can produce with the learning algorithm. It might be, for example, that the space of all neural network is very big. It's the combination of all the weights of the parameter configurations. Okay, but when you couple this space or this architecture with the learning algorithm, actually the learning algorithm will have an effect on the possible functions that you can possibly reach. Okay? I will elaborate on that later, but that's something you should pay attention to. the hypothesis space is not only just the set of all possible configuration of a model, it's only those that you can reach with the algorithm that you use to train it. Okay, so, but regardless, let's say that F is this hypothesis space. Now what we want is that among all these functions that we can possibly obtain, we are looking for a special function which belongs to this space, and we are looking for the function with the smallest expected risk, okay, or the smallest generalization error. And how do we define this expected risk? We'll define the expected risk of some function f as the expected value of the loss over the distribution of the data. Okay? So are you all familiar with all these symbols? If not, please tell me, because I will keep using that over and over. So this E means an expectation. Then you have this, which means the distribution that you use to expect over. And then for each realization out of this distribution, you compute this quantity. Okay? And in this case, it's just the loss between the ground truth and the prediction. Okay? So now, if we can define this notion of unexpected risk, now we have a way to define what we mean by a good function and also what we mean by the best function we could hope to obtain. And in this case, the best function we could hope to obtain, so the optimal model, will be the function f star for which the expected risk is the smallest. Okay? So far, so good. Now, the big issue is that we don't have access to this distribution, so we can't directly evaluate this expectation. So we know how to define the optimal model that we are after, but we don't know how to find it because we don't have access to this distribution. The only thing we have access to is a data set, a subset, a random subset that you've generated from this distribution. Okay, so since this distribution is unknown, the expected risk cannot be evaluated, and so because of this, we cannot determine the optimal model. Okay, so the thing we'll have to use instead is the training data. And with the training data, what we can at least do is to compute an estimate of the expected risk, and this estimate will be an empirical estimate, which we call the empirical risk, okay, which will be simply an empirical average of the loss, and you compute this empirical average using the training data that you have. Okay, so you replace the expectation over the distribution by an empirical mean that you compute over your data set, and you just, for every input-output pair, you compute the loss, and then you just average everything. Okay? So this is an estimate of the thing we are trying to minimize, but this is not the same quantity. Okay? Nonetheless, this estimator is an unbiased estimator. Okay? And we can use that for finding a good enough approximation of f star, the optimal model. And this overall results in the final recipe, which we call the empirical risk minimization principle. Will say that the function that we'll try to estimate is the function f star d, where d denotes the dataset that we use, which is a function f in our hypothesis space, which minimizes the empirical risk r hat, okay, over the dataset t. Clear for everyone? Questions? What do I mean by an unbiased estimator? Yeah.
If we have all the possible training data in the universe and training data, it will lead to the same optimal function.
No, that's not what a bias. So when do we say that an estimator is biased or unbiased? Yeah.
So it's so far from the actual value.
When it's not too far?
We say it's unbiased if it's not too far from the true value of
That's not what that means. Yeah.
On average, with multiple dataset, it will find the real value, but the expectancy, it will be close to.
Yeah, that's almost it. So when we have, so what you should realize is that an estimator is just a formula which corresponds to a random variable, okay, which can take several values, which we call the estimates that we use, okay? So this empirical risk is itself a random variable. If you change the training data, you will get another value. Okay, if f is fixed, and the only thing that you change is d, the data set, then you will get another value. Okay, so you should understand that the empirical risk is a random variable. Okay, it's trying to estimate this expected risk, but it's a random quantity, unfortunately. But what I'm saying is that the estimator, so this formula, is unbiased, meaning that if we were to look at the expected value of the empirical risk, if you would take instead the expected value of the empirical risk, which I've defined as fd, and you take the expectation over the data sets themselves, okay, I'm saying that this estimator is unbiased when the expected value is equal to the expected risk. Okay? And if the expected value of the empirical risk was not equal, exactly equal, then we would have a bias estimator. Okay, so when it comes to machine learning algorithms, many of them, if not all of them, and that includes neural network and deep learning, will implement some sort of empirical risk minimization principle. So this recipe, even though simple, is really at the core of what we do. And what is also nice about this recipe is that not only it's unbiased, but, and that's a bit more important, under some regularity assumption, the empirical risk minimizer will converge to the expected risk minimizer. Meaning that as you increase the size of the data set, eventually the solution that you find by minimizing the empirical risk on your data set, as your data set gets larger and larger, the solution will eventually converge to the optimal model that you have in your hypothesis space. Okay? So basically, this is saying the larger the data set, the closer you will be to this behavior. Okay, so just to instantiate this recipe, let's consider a very simple problem, the problem of polynomial regression. Okay? So we'll consider that in this case that we know the joint probability distribution. Okay, so just a toy example where everything will be under control. And this joint probability distribution over the inputs and the outputs will be induced by the following data generating process, where we'll say that a random realization of x and y from the joint is the same as first drawing some input values uniformly between -10 and 10. Okay, so you just draw a number in this range, in this interval. Then you draw some random Gaussian noise epsilon for some fixed variance sigma square. And then we say that y, the output value associated to x, is the result of the evaluation of g, some unknown polynomial of degree 3 in this case, plus the noise epsilon that you've generated at the previous step. Okay? So you can repeat this many times, and that will produce many pairs of inputs and outputs. Okay? And that's the data set that we'll use to try to train a machine learning model. Does that make sense to everyone? Okay, so you see there an example. In red, you see g of x, the polynomial of degree t that I'm using to generate the data. In practice, of course, we'll not know about this red curve. Okay, the only thing we'll get access to are the blue points that you see also on the same plot. Okay, so what should we do then if we want to find a good approximation of this red curve, if we were to follow the empirical risk minimization principle? So what's the very first step we have to do? Yeah. Okay, we have to define an hypothesis space. We have to define the class of functions we'll consider. So what could it be in our case?
We fix some large n, and then we have the set of all polynomials of degree inferior or equal to n.
Okay, we could do that. That's exactly what I did there, except I set it to a maximum of 3. Okay, but we could say we just consider for our hypothesis space the polynomials of degree up to 3, okay, which we can define with 4 parameters, the coefficients that you put in front of each of the xd elements that appear in the polynomial. Okay? So this is our hypothesis space. Then what? We have a data set. That's the blue points. What do we need next? So just for everyone, so we'll want to find this function okay, and this is itself defined okay, so this is what we'll try to minimize. So far we have defined, so that we know. What do we need to define next?
We need to find a suitable loss function.
Okay, we need to define also loss. What could it be in this case?
The square.
Yeah, we could use, for example, the squared error, where we'll say that L, Y, and Y hat is, for example, the square difference between the two. Okay? So this is what I have in the slides. Okay, and if you put everything together, then we arrive to this objective, where I've replaced the search over functions into a search over parameters, configurations of the parameters of the function, but this is strictly equivalent. Okay, so instead of, you see that in my notations I have f of x and then w. W are the parameters of the polynomial, which you see appearing there in front of each of the powers. Okay? But so that means you can use that also to replace the search, so the minimization not over the functions themselves, but over the parameters of the functions. Okay, so we replace, in this case, this by the parameters w, and we'll be trying to estimate the optimal parameters, w star. Okay? Okay, so this is the thing we want to minimize. Okay? This is framed in terms of the expected risk. We don't have access to the expected risk. However, we can use the training data. to define the empirical risk, as I did already on the blackboard. And so we'll be trying to minimize R hat instead of R, okay? This is the empirical mean of the squared error of the predictions, okay? F, because of the shape of, the choice of F that we've made, we have said these are polynomials. Okay, we can rewrite F in this way. And finally, we can rewrite everything into vector and matrices operations. Okay, and we are back to this problem. Okay, so this is the objective. How do we find W? Yeah.
We can use quadratic descent because we want to find a minimum and we know that the gradient will be 0.
Yeah, so you could, and that's the recipe we'll use in deep learning. So you can use a numerical optimization algorithm to find a good enough approximation of W star, okay, using, for example, gradient descent. In this case, because the objective is convex with respect to the parameters, we can actually find the optimal solution in closed form, okay? And in this case, we would have that W star D is given by this expression, okay? So you don't need any numerical optimization. In this case, you can be a bit smarter and directly compute the optimal solution in one go, okay? If you do that, then what we'll obtain is the curve in blue, okay? We'll find some parameters WD star, which we can plug back into a polynomial, and when we plot this polynomial, we get the curve in blue. What's your opinion about that solution? Remember, in practice, in reality, you don't get to see the red one. Yeah.
It's a good one based on the data we have.
Yeah, it does not seem too bad. It fits with the data. It's not perfect, nonetheless. There are many data points that are not fitted that well. Actually, maybe there is only one or two or three, these ones, or four maybe, where we have the polynomial passing exactly through the points. One thing we can do, because this is a toy example, and everything is under our own control, is to check if really that's true, this thing that if we were to increase the size of the data set, we would converge to the red curve. Okay, I've told you that, okay, under some assumptions, the empirical risk minimizer will converge to the optimal model. That's something we can check. Okay, so if you apply this recipe and the only thing that you change is the number of training points, the size of the data set D, what we should see, hopefully, is that the blue curve converges to the red one. Okay, so we can verify that. This is the solution we would obtain for a data set of size 5. We are not there yet. 10, 50, 100. We see it's closer, but still not exactly the G polynomial. And if you increase to 500 points, you get something which is very, very close to the G polynomial. Okay? That seems to work, and it's quite good. Okay, now the question you may ask yourself, but how do we know in advance that you should pick a family of polynomials of degree 3? If the only thing that we see are these blue points. We could have used polynomials of degree 2, 1, 4, 5, 10, 100 if we had wanted. So how do we make these decisions? So what do you think will happen if instead we had used a a family of polynomials of degree 2. So just parabola. Yes.
We will underfit the point.
Okay. What if we had used polynomials of degree 10?
Captions to try to I don't know what is called in English, but it will overfit.
Okay, it will overfit. Okay. How do you know it's underfitting and overfitting? Yeah.
Because it's of the variance and the bias of
Yeah. Yeah.
When we overfit, we fit the point of the given dataset. So we have a very dataset dependent and two given prediction will be very different to each other.
Okay, but I mean, if you all paid attention, that's what we want to do. We want to find a function that will minimize the loss on the dataset. So as the lower this quantity, the better. No? Yes?
Yes, but we also have random noise that comes because we have a physical phenomenon, and so the data we collect is subject to that noise.
Mm-hmm.
If we are only basing ourselves on fitting all the points, we are also fitting on the noise, which is not what we're trying to do because we only want to fit on the model.
Okay, but you are making assumptions. How do you know there is noise? You only see the blue points. No? Yeah, I agree with you, but you should realize you are making additional assumptions, which are not there in this equation. Are they? Yes?
We need to add a test step, divide our data set into a training set.
Okay. And what will you do with that?
What?
What will you do with the test set?
Verify if on ANSYS data the model will still give a good prediction.
Okay, but why don't we just care about this one? Since this is the driving principle for us.
Because the idea of doing this is to be able to generalize the new data that we don't have, and in this case, if we fit that, it will not work well.
I mean, I've shown you it will, as you increase the size of the data set, the empirical risk minimizer will converge to the correct solution. Are you saying I should do something different than that? That minimizing my training error?
But here we assume that the degree of the polynomial was 3, but this is something we...
Yeah, we could have picked something else, I agree. Okay, so all these concepts, I think you know them, but it's maybe a bit... I mean, you have forgotten maybe some parts. So let me recap up the story of underfitting and overfitting. So the question is, what if we consider an hypothesis space F in which candidate functions are either too simple or too complex with respect to the true data engineering process? Then you have said correctly that we may be in a regime where we underfit or we overfit. But that's only when we know what is the true data engineering process. In reality, you will not know about that. Okay, let's start with an example. Let's say this is the data that you have. I'm giving you the name of the input. They correspond to year. And then you have some quantity that you associate as output. That's the only thing you know. You don't know, you have no assumptions about how this data was generated in the first place, but you will try to fit a machine learning model to this data. Very simple question, which model would you choose? So raise your hand if you would go for model F1 in which you would just be fitting a line. Okay, half of you. Raise your hand if instead you were picking, like before, a polynomial of degree up to 3. 1, 2. And what if instead you pick a polynomial of degree up to 10,000? Who would go for that? I would go for this one. And actually in deep learning, that's what we'll do. We will train models that have billions of parameters. Many more than the size of the training set. And why am I picking this family? It's because certainly in all these parameterizations, there is one which will fit the data. And actually this family of models can fit everything that F1 and F2 can also fit. So why should I restrict myself to a family of polynomials when I can go beyond linear models or polynomials of degree 3?
But you are risking of overfitting the data.
Yeah, but that's something else. Okay, maybe I will also implement together with that proper validation strategies, or also I will make sure that I will use an optimization algorithm that will prevent me from overfitting. Okay? And so this is related to what I was saying before. The hypothesis space is not only, so in this case would not be only the set of possible functions that we can represent in this way. Okay? The hypothesis space is only those functions that you can also obtain with the optimization algorithm that you use. If you use stochastic gradient descent to tune these parameters, actually you will not be able to reach all possible polynomials. Okay, but so let's see. If we fit a linear model to the data from before, we would get a straight line, of course, and it would not be very good at predicting the training data, and we would have an empirical risk of 640. If we consider polynomials of degree 2, well, of course we get a parabola, which in this case is oriented in this way. And we do see that, yes, actually the empirical risk is lower than before. We go from 600 to 400. If we pick a polynomial of degree 3, then we would have an empirical risk of 43, which is even better. Okay. But, okay, since the goal is to minimize the empirical risk, I could also consider polynomials of degree 4. I will obtain this blue curve, and in this case, the risk that we find for the optimizer is 37, which is strictly smaller than 43. You all agree with that? Okay, and we could go on. If I pick polynomials of degree 5, I would have an empirical risk of 29, which is better. And if I pick a polynomial of degree 10, I would have an empirical risk of 14. And if you make a plot of the degree of the polynomial for the x-axis and the training error on the empirical risk on the y-axis, then we would have a decreasing trend. As we make the polynomials of higher degrees, we get better results, in terms at least of the empirical risk. So why shouldn't I pick this model? The value of 10. That's the one that minimizes the empirical risk. Yes?
Because it might be overfitting the data.
Okay, what do you mean now by overfitting? Can you describe that?
Having a training error that is smaller than the test error.
Okay, where is the test error there? What do you mean by the test error? Okay, what's the test set?
Is the hiding data that we didn't bring the model on.
Okay, I've not done that yet. So why should I do that in the first place? Why should I put some data apart for testing? Yes.
The problem is that we measure the error from the data we are fitting on, and so we don't measure the error of the model from unexpected data that he has approximated.
Yes, exactly. So, where is it? So what you should realize is that, okay, if we evaluate this quantity on D, the training data, this quantity now, contrary to what I've said, is a bias estimate. Why? Because F depends on D. Okay? If you remove this and say you will use FD star there, and you remove that, okay? This quantity now is a bias estimate of the expected risk, because this function depends on D. Okay? So that means these estimates of my expected risk, okay, I cannot use them actually to correctly assess the quality, the actual generalization error, meaning this guy, the expected risk. Okay, and therefore, if I was to pick this model instead of something else, then I would be fooling myself because these values, they are biased. Okay, and so that's why we need to put some data apart, a test set, which is not used at training time, which is not used to identify this function, so that then when you will evaluate this quantity over this independent set, because you've broken the relationship between this data set and this one, okay, now you will get an unbiased estimate. Does that make sense? Okay, so to get there, let me first introduce the notion of the base optimal model. So let's first consider the set of all possible functions. So, and when I say that, it means all possible functions, including those that are not part of the hypothesis space. So all possible mappings from inputs to outputs. Given this set of all possible functions, we'll define the base risk as the expected risk that we can reach by picking the function from this set of all possible functions and picking the one which minimizes the expected risk. Okay? And we'll call FB, the function f that attains this minimum. Okay? Or the base optimal model. And so if FB has been picked among all possible functions, and we pick the one which is the best, then that means no other function can do better than FB, obviously. Okay? This also means no other function can reach an expected risk which is smaller than RB. Okay? Okay, now remember this concept. Now I will define the capacity of an hypothesis space, which is induced by picking a family of, or picking a parametric model together with a learning algorithm. And so the capacity of an hypothesis space will represent the ability to find a good model F in this space, regardless of the complexity of the task. Okay? So in practice, capacity can be controlled by, for example, expanding the set of functions in the parametric family that you consider. For example, by saying that you go beyond polynomials of degree 3. You could go to 10,000 if you wanted, and you would therefore increase the capacity. In the case of a neural network, you could, for example, adjust the number of layers, the number of neurons that you have in a layer. But you can also change things that have a direct impact on the optimization algorithm. For example, you can change the number of training iterations if you are using stochastic gradient descent. Okay, so for example, it's very easy to understand. If you take this space of polynomials of degree 10,000 and say, together with that, your algorithm is to start by setting the coefficients to 0 and then you are allowed to 3 steps of gradient descent, of course, you can understand you will not be able to reach all possible polynomials. Or you can also add regularization terms to the actual loss that you minimize. But we'll talk about this in other lectures. Okay. So for now, just consider this concept of capacity. And then once we have this concept of capacity, we can properly define underfitting and overfitting. And so if the capacity of the hypothesis space is too low, then because of that, certainly the optimal model will not be part of your hypothesis space. Okay. It also means that the expected risk, the difference between the expected risk and the base risk will be large for any function of your space. Okay, so whatever you do, whatever function you pick from our hypothesis space, all of them will have a risk which is far from the optimal risk. That's what that means. And when you are in this regime, then we say that the models F, they underfit the data. Okay, on the other hand, when the capacity of your hypothesis space is too high, then we can have several things. If it's too high, then actually that can be a good news, because in this case, it's more likely that the optimal model is also part of your hypothesis space. Okay? And what can also happen is that the difference between the expected risk of the best function among your hypothesis space F star and the base risk is small. Okay, it can be that, so either the base risk is part of your hypothesis space, in this case this quantity will be 0, or it's not, but that's okay still, because the very best function that we'll have among this hypothesis space will be such that the difference between the two risks will remain small. Okay? However, so that's a good news, that's why you should increase capacity. However, because of the high capacity of the hypothesis space, what could also happen is that the empirical risk minimizer, so FD star, the function that you find when you minimize the training error, could fit, as you have said, the data too well. It will fit the noise, as you have said. And when that happens, what we will see is that the empirical risk of that very best function will be smaller than the expected risk of the optimal model. So when you are in this regime, you are fooling yourself because you think this, if you were to use this quantity, that you would obtain very good model. Okay? But that just actually indicates that this empirical risk is actually not a good estimate of the expected risk of the empirical risk minimizer. Okay? Because when that happens, usually what will also necessarily happen is that since no other function can be better than the base optimal model, we have that the actual expected risk of the empirical risk minimizer is larger than RB. Okay? And so this is, when this happens, this is where there is a danger. Of course, can be quite tricky to diagnose because we don't have access to this quantity nor to this quantity. The only thing we have access to is this quantity, at least at training time. Okay, but when that happens, then we'll say that F, or the empirical risk minimizer, will overfit the data. Okay, and so if we combine these two regimes, the goal for us will be to adjust the capacity of the hypothesis space such that the expected risk of the empirical risk minimizer will be as low as possible. Okay? Okay, but how do we do that if we don't know the expected risk of the empirical risk minimizer? Okay, so as I've told you, you should not use the empirical risk minimizer itself, the empirical risk itself that you evaluate on the data, because this is a bias estimate. okay? Because the function of D is tied to D itself, okay? So what we can do instead is to use data which has not been used to find the empirical risk minimizer, like a test set. You leave out a part of your data set for testing purpose, and you don't use that for training. And then you use this test set then to build an unbiased estimate of the expected risk, okay? Which I denote in this way. So it's the empirical risk of the empirical risk minimizer, but which you evaluate on some other data set, D test. Okay? And what is nice is that this test error, okay, it's an estimate again, but this test error is an unbiased estimate of the expected risk of the empirical risk minimizer. Okay? And if we do that for our polynomials, then we would have now the second curve in blue, where I've shown you the test error. And now that you see that, what degree D should you pick for the polynomial? One, two, three, four, five? 3. Okay, you pick the one for which the test error is the lowest. In this case, 3. Okay, if you pick 3, and you should really pick 3, okay, and you follow this recipe, you divide your training set into 2 parts, training, test. Okay, you do your trainings, you scan over these hyperparameters for the degree. Okay, you do this curve in red together with the one in blue. Okay, then, as I've told you, you should pick the hyperparameter which correspond to the lowest test error, because they are unbiased estimate. And then you write your report or you write a scientific paper. What should you write when you comment on the performance of your model? What values should you report? Should you report the training error or the test error? The test? So who says the training error? If you have to give a number telling to convince someone, okay, my model is overall 90% accurate, let's say. Okay? At training time, you would have, let's say, 95% accuracy. On your test set, you would have 90% accuracy. So should you report as the actual performance 95%? No. Should you report 90%? Who says yes? A few? Yeah? What about all the others? Yeah.
I think we should report the two because the training set, the two value depend on training state and test set. So it's data dependent.
Yeah, so it's a good idea to report everything. I agree with you. Anything else?
If the model selection was made on the test set, we should report none of them.
Yeah, correct. Okay. Since we use the test set to make a choice, we are using the test set as training data. So this estimate, even though certainly it's not that far from a good estimate of the actual generalization error, it is biased. Okay? It might be just a random fluke. Okay? And if we had another test set, maybe we would have made another decision, or maybe the performance that we see would be slightly different. Okay? So as soon as you use the data to make a decision, that becomes part of the training set. And so this performance becomes biased. Okay, so what you should do instead is to divide your data set into 3 parts. Training, validation, test. Or use the training data for actually training the parameters, the validation data to make this selection, and finally the test data to have an unbiased estimate of the actual performance. Do you remember that now? Okay. Okay. So this is what you have in the following slides. So the evaluation protocol could be something like this, where you work on your model, you train and use the training data, and you iterate maybe several times, and once you are satisfied with your result, you stop, and you really stop. Then you assess the performance on the test set, okay, and you report that in a paper. That's correct, okay? But what could happen is that you are maybe overfitting, but the actual performance evaluation is not biased. Okay, but you may certainly you are certainly suboptimal because you have not used a validation set. What you should really avoid is something like this, where you work on your model, you train, you iterate, then you are curious, then you test on your test set, and maybe you test several models, and then you can't help yourself but compare the results and maybe iterate back and improve the models. If you are doing that, then this test performance becomes biased. Okay, and the actual performance is certainly not what you think you are reporting. Okay, so please never ever do that. The proper evaluation protocol should be something like this, in which you have now divided the dataset into 3 parts: training, validation, test. Use the training set to train your model, to find parameters. Then you use the validation set to guide the search or the choice of the hyperparameters. Then you iterate maybe several times. Eventually you pick the configuration for which the validation error is the lowest. And once you are done, and only then, you evaluate your performance on a test set. Okay? And in this case, the performance will be unbiased. Questions on this? Yes?
So if you want to improve the test, you have to split with a new dataset?
What do you mean to improve the test?
Well, if you did like the result,
Yeah.
and you don't want to rewrite the code, so you have to have a new dataset?
In theory, yes. In practice, no one is doing that. So in practice, what happens is that this loop is repeated across several papers, and we are all comparing our models on the test set to say, okay, this one is actually better, this is state of the art. But that means when we do that as a community of researchers, we don't know then anymore the actual performance of the model, because the choice of the best model has now been guided by this test set. Okay? There is maybe also an interesting new version with this protocol, which is something which is not very new. But one thing you should also realize, and specifically with large language models that we'll see later on, but these models that are used to train these chatbots, because they've basically seen the entire internet several times, it's very likely that in almost all benchmarks that maybe you are seeing, the test set is part of the training set. And so that's a big issue, actually. To properly assess the quality of this model, we have a problem because they've been trained or So you can either train yourself one of these large language models, but certainly you don't have the resources to do that. And in this case, if you want to use one of these large language model to do something, you download a pre-trained model, and then you do your task, and then you test. But certainly your test set will have been part already of the training set of the pre-trained model, except you don't even know it, which is even worse. So this is a big problem when it comes to the evaluation of these models, because basically the test set is leaking into the training set. Okay. So how many slides? Okay, let me go to the end. Okay, so we have talked about overfitting, underfitting, through the concept of capacity of an hypothesis space. Related to that is the decomposition in terms of bias and variances. So this should be just a reminder, but I think it's important. because that's a nice characterization. So if we consider, at least for this next few slides, just a regression problem, and we consider a regression problem only at a fixed point x. Okay? And we consider the prediction y hat that we obtain by the empirical risk minimizer fd star, which we evaluate at x. Okay? Then I will define the local expected risk. When I say local, it means that I only care about predictions at x. Okay? And so this is defined similarly as the expected risk, but where I restrict the expectation over the conditional of y given x instead of using all pairs of y and x. Okay? But the quantity inside is the same. Let's say it's a regression problem. I will use as a loss the squared error. Okay? So the local expected risk is the expectation of this quantity. This can be then rewritten as in this way, as a sum of the expectation of the squared error between the actual value and the very best predictions we could hope to obtain if we were to have the base optimal model FP, plus the expected deviation of the prediction to the prediction of the base optimal model. Okay, so I'm just rewriting the error as a sum of the error that the best model will make together with the deviation to that best model. Okay? This quantity is something we've already defined, at least unconditionally. It's the base risk. Okay? In this case, the local base risk. Then you see this, which is the expectation over the y value of the squared difference between the predictions. You see that the inside of the expectation do not depend on y, so that means we can rewrite this expectation simply as the square difference between the base optimal prediction and the prediction given by the empirical risk minimizer. Okay? So now that means the local expected risk can be written as the local expected risk of the base optimal model, okay, which is this quantity. And what we should realize that this quantity will not be able to reduce it. Okay? If the best function can have a base risk which is larger than 0, then we'll not be able to do that. Okay? And the second term, as I said, represents the discrepancy between the best model and the model that we find. Okay? So this is not yet the bias variance decomposition. What we need to do to go to the bias variance decomposition is to look at this expression in expectation over the data set. So what we should realize is that if we were to repeat this experiment over another data set, we would obtain other values. Okay? And if we add yet another data set, we would have another value. So that quantity, here at least, is itself a random variable. Okay? So the empirical risk minimizer is a random variable, together with its prediction, and together, but that was already the case, with the empirical estimates. Okay, so for example, if we go back to our problem and repeat this experiment of fitting a polynomial of degree 1, and we repeat that for many datasets D that we can generate with our toy example, we would get many different solutions, okay? And if I was to average all these solutions, we would obtain, or rather, if I was to average the predictions, we would obtain the line that you see in blue. And you see also a band which corresponds to some kind of standard deviation to that mean. Okay? What do you observe? What does this plot mean to you? So to me, it means that regardless of the data set, will always do a poor job. You see that none of these lines fit well with the red curve. You see also that actually the data set, I mean, we get some variations, but it can be quite limited actually. It's some deviations around this mean, and okay, we always have an increasing trend, maybe slightly more tilde or not, but it's more or less always the same. Okay, in this setting, we are, as we have said, underfitting, but it's also in this setting where we are biased. So regardless of the data set, we are always wrong. Okay, we are always different from the red one, so we are biased. Okay, but the variance maybe is limited. You see that the variability of the solutions is contained. If we repeat that for polynomials of degree 2, we get something like this. Again, we get many different solutions. Most of them are going upward, but maybe some of them are going downward. Again, we see that it's quite biased in the sense that regardless of what we use as a data set, it's always bad, and on average it's bad. Okay, the blue one is not matching with the red one. We also do see that, or we can notice maybe a bit that the variance maybe is now a bit larger. Okay, we get more variability in the solutions. If you compare, for example, the size here of the bands with respect to before, okay, these ones were smaller than for this case. For polynomials of degree 3, we would get something like this. What do you observe? Looks good. Why? Is it biased?
It's not really biased because all the blue are close to the red, and the variance is pretty low because it's always those.
What do you mean? Why do you mean? Why do you say really? You say it's not really biased. So do you say it is biased or it's not biased?
Well, to see if it's biased, you need to take the appearance of all the blue lines
And you get the one in plain blue, in dark blue, if you were to do that.
and it will be slightly biased because there will always be a difference between the
Yeah, it's because here I'm just estimating this expectation, but if I were to repeat that for infinitely many training set, the blue and the red one would be matching exactly. So it's not biased in this case. Okay? What about the variance of the solutions? It's okay, yeah. Okay, but we could have picked a larger family of polynomials, like a family of polynomials of degree 4. What do you see? Is it biased? No, it's not, for the same reasons. But what about the variance? It's larger. Okay, you can see that the size of the contours to the left or to the right are much larger than here. Okay, it's because when we consider this polynomial, if you have only a few points, that will impose very few constraints on that part of the polynomial. Degree 5 would have something like this. Again, it's unbiased, but now the variance is even larger. Okay, so this is really an illustration of the bias and variance decomposition. And so formally, we can also derive that, where we look at as before, we look at the local expected risk, but we'll do that in expectation over the dataset D. Okay? And now when you consider this quantity, well, we have derived before that the local expected risk can be rewritten as the sum of the base risk and the systematic discrepancy. We can move this part out of the expectation because it does not depend on D. We are left with this. And this can be further written as a sum of two terms. The squared difference between the Bayes prediction and the prediction of the average model, or the expected empirical risk minimizer. That makes sense. Okay, which is that blue line that you see there. Okay, and this quantity is what we call the bias, plus the variance of the prediction, which we define as the expectation over the data set of the square difference, so the systematic discrepancy between the prediction of the expected empirical risk minimizer and the empirical risk minimizer itself. Okay? And this is the bias variance decomposition. Okay, so how does this relate to what we have seen before? Well, we have now a bias variance trade-off. Reducing the capacity of the hypothesis space will make the empirical risk minimizer fit the data less. Okay, this is what we have seen when we consider polynomials of degree 1 or 2, which will have as an effect to increase the bias. However, so we could say then we'll just increase the capacity, because if we lower it, we'll increase the bias. But that's where this becomes tricky. If you increase the capacity, of course, that will reduce the bias, and eventually you will get a bias which is equal to 0. But at the same time, increasing the capacity also increases the variance of your predictions. Okay, so it's a matter of finding the right trade-off between the two. Okay, now, question. What if I consider a neural network with millions of parameters? And to be a bit more precise, whoops. Let's say I have a neural network that takes X as input, then map this to a layer. That's something we'll see next week. Okay, and then produce an output. Okay, and I will define this quantity as Hj, which will correspond to some activation function like a sigmoid or ReLU or whatever. This is not important yet. Of some Wj, some coefficient, times X. Okay, so I'm just basically rescaling the input many times, as many times as I have elements in this, what we call layer. Okay, and then I will say that Y is equal to a big weighted sum. So this is for 0, this is for 1, over the J of the Hj. Okay? So I'm just doing a big weighted sum, and in between I have these activation functions. Okay, that's what we call a one-layer MLP. We'll go slowly next week over this model. But the question I'm asking you is, what if I'm using this model to fit my data, and I say that the size of this layer is 1 million. What do you think we will obtain in terms of the predictions on our problem, where we have to classify these points? So on this. Yeah.
So structures of the F space is like very different now, because
before we use polynomial
Yeah.
space, and the function happens, the function approximated happens to be a polynomial. Now we just having linear combination.
No, it's not, and it's not linear because of this function, which is a non-linear function.
Okay. But it's combination of this function.
Yeah, but you have a linear combination of non-linear combinations of the input.
And maybe it won't work very well.
Okay, so let me ask you something. So, does this network does it have high capacity, according to you? If we put 1 million parameters, it should have high capacity, right? If it has high capacity, we are risking overfitting. Certainly with bias which is small, but we can have high variance, as we've seen. Okay. So what do you expect the model? How do you expect the model to fit these points? Yeah.
To try to meet every single point.
To what?
To meet.
Okay. So maybe something like this.
We can see.
Hop. Raise your hand if you think this is what will happen. So at least one. Okay, you may be telling yourself if he is asking that question, it should be different, but would you expect that? Would you have expected that? Many parameters, you will get something like this which fits the data very, very well. That's the story you have been told, right? Okay, if you do that, and you can do that, you will be able to do that yourself next week. If you train a one-layer MLP with 1 million neurons on the first layer, you will get something like this. A very smooth function, which do pass through some of the points, but which is nothing like something like this. Why? If I'm crazy enough to use 1 million parameters, I should overfit my data, right? It's not overfitting. So yes?
Are you penalizing the complexity of the model?
Nothing. The complexity of the model is fixed through the architecture. Yeah.
Maybe because the white solution is not in F. Because when we were using polynomials, the true function was in F.
No. No. Actually, I could complement this with other inputs like x squared, x3, x4, and add them as inputs. You would have also something very similar to that. Yeah.
Is it because of the activation functions that are used in each neuron?
No. The activation functions, of course, are very important, and the role that they play is to produce these non-linearities. Okay, but even though I have 1 million of them, I have nothing as crazy as that. So basically, what I'm showing you is that I've trained a neural network, which is of this kind, even larger, and it works. Why? Yeah.
You didn't train too much the neural network?
Okay, that's something I've not told you, is how do you actually train this neural network? How do I find this parameter W to find this solution? It's not that I've not trained long enough, when you train a neural network, you use stochastic gradient descent, which is a randomized version of gradient descent. We don't try to find an exact solution, only an approximate one. And one of the properties of this algorithm, that's something we'll see in a few weeks from now, is that because of this stochastic algorithm, naturally will emerge this regularization property, and will not be able actually to find, even though maybe certainly there is a configuration of the parameter of the neural network such that we could represent this, we'll not be able to find it because of the learning algorithm that we use. Okay, so actually the hypothesis space does not include this one because of the algorithm that we use to find the parameters. Okay? Okay, there is also something a bit more crazy about deep learning. Okay, let's consider the case where I will make a plot where the x-axis corresponds to the number of parameters of my neural network, of my model. And I will plot both the training error and the test error. Okay? As you increase the capacity of your network, or rather, as you increase the number of parameters, we expect the training error to be smaller and smaller and smaller, and maybe eventually to reach 0 if we can. Okay? If, together with the train error, I plot a test error, the story is that I've told you is that, okay, we'll get something like this, but as we increase the capacity, or the number of parameters, we'll be in a regime where we have too much capacity, and we'll overfit the data. Okay, so think about this. I've been telling you from the very beginning, in deep learning, we train models with billions of parameters. Why don't we overfit the data always? And the reason, and it's still a bit mysterious, even though we start understanding this, is that actually, if you make an experiment and increase the number of you keep increasing the number of parameters, what do you think will happen? It goes up, but eventually it goes down. And why is that? It's because the number of parameters is a bad proxy of the actual capacity. When you reach a regime where you have too many parameters, but you couple that to an algorithm like SGD, actually you start decreasing the capacity. And so we get this curve, which we call the double descent curve, in which we have the classical story. Okay, the training error, the training risk decreases, the test risk decrease and then increase, but eventually there is a point beyond which the test error decreases again. Actually, this plot, or the label associated to this plot is wrong. It should not be capacity, okay? It should be the number of parameters, okay? But you can indeed find empirically papers where they report these kind of results. So on the x-axis, you have the number of parameters. On the y-axis, you have the error. In blue, you have the test, and orange, the train. And you see that there is a point beyond which the test error starts decreasing again. And again, just to stress why this is happening, is because when your parameters when you have so many of them, eventually, adding more and more of them will regularize the solution that you find, will reduce the capacity actually of the hypothesis space, and you will get, escape this overfitting regime. And so you will be decreasing the test error again. And what is nice actually is that when it starts decreasing again, you may, and usually that's what happens, you reach a regime where the lowest value of the test error beyond this point is even better than the lowest value that you had in the first part of the plot. Questions? No? Okay, then that's it for today. See you next week.